Well, welcome back to my channel. In this video, I'm going to take you through equations of lines in 3D. 3D, I mean three-dimensional space. So, in our journey into the three-dimensional space, let me introduce to you the axis of a three-dimensional space or the three-dimensional axis. So, when you say three-dimensional space, we have three axes acting at 90 degrees to one another. So, we have the y-axis, we have the z-axis, then we have the x-axis. I hope you are familiar with x and y-axis, which is the two-dimensional. Now, you can see that the presence of the z-axis here introduces the three-dimensional space, right? Okay, so now, whenever you have a three-dimensional space, you are going to have three two-dimensional space acting. You have the xy plane, you have the xz plane, and you also have the yz plane, right? So now, how do you find the equation of a line which is in the three-dimensional space or which is in space, right? How do I find the equation of that line? So now, let me draw the three-dimensional space. So this is z and this is the x, this is the y, right? Generally, you know that whenever you want to find the equation of a line, you need at least 2 points on the line, or you need a direction and 1 point. So if you have any of these two conditions, you should be able to find the equation of a line in three-dimensional space. So the first one is you should have at least 2 points, and the other one is a direction and also 1 point. In two-dimensional space, let's say the xy plane, right? When I have my x and my y, to find the direction is very easy. That's what we call the slope, right? But now I have three different planes combined together to give me my three-dimensional space. So how do I find the direction? We introduce a new vector which we call the direction vector in this manner. So the new concept here is we introduce what we call the direction vector to fully define the direction of our line. So now let me give you a pictorial view of what we're going to do. So this being our z-axis again, this being our x-axis, and this being our y-axis. I'll have 2 points, a point p naught, and a point, let's say, p, right? So these 2 points can be connected to the origin to give me the position vectors of what? P naught and P. So this is O. So I'm going to get here to be what? Position vector of what? P naught, position vector of what? P, right? Then I can join my 2 points to give me the line I'm looking for. So joining my 2 points, this is the line I want to find the equation, right? This is the line I want to find the equation. Remember that whenever you have 2 points, the line joining them is the line of interest. That is the line we want to find its equation. But to fully define this line, I said we need an external vector which will define fully the direction of this vector. Therefore, that vector will have the same direction. So we introduce a new vector which is parallel to this as v, right? Yep. So once you have this, now we will let the position vector of our p naught to be r naught. That's the position vector, vector r naught. Then the position vector of our p to be vector r, right? So you know that you have our arrows on it. So at this point, how do you find the equation of our line? Our line now is the vector p naught p, right? So our line, that's the equation of the line, is simply equal to the vector P naught P. So what the vector P naught P? The vector P naught P is the same as the position vector of what? P. The position vector of P, right? Minus what? The position vector of what? P naught, right? So now P naught P is giving us position vector of P minus position vector of P naught, and position vector of P is giving us what? Our R minus our P naught, which is equal to R naught, like this. So at this point, you realize that we are getting an equation of the line, but how do we define P naught P? So now this P naught P, as we said, is parallel to what? Our directional vector, which is what? V. Is that not it? Yes. In vectors, whenever two vectors, let's say vector A and vector B, when you say that they are parallel, meaning that one is the multiple of the other, right? So meaning that if this particular line is parallel to our directional vector, the relationship between these two is that they are a multiple of each other. So if they happen to be equal, then we say that they are equal. Is that not it? So I can represent this vector here as the multiple of my directional vector. So I'll make it, let's say my directional vector is going to be what? Let's say A, right? So I'll multiply this by an unknown, which is T, right? Yes, so at this point, AT is equal to, so this is the vector A, being my directional vector. Then T is just a variable I have put there to quantify the parallel nature of what? The vector. So this is equal to R minus R naught. So now I need R. R means that you want to find the vector when you have P naught and you have your directional vector A. So meaning our R generally is giving us R naught plus vector AT, and this gives us our vector equation of a line. The vector equation of a line. Vector equation of a line. So have this equation in mind. R naught plus vector AT is equal to R. So now let's see. So assuming that our R is equal to an unknown X, Y, and Z, right? And our R naught is giving us a known X naught, Y naught, then naught, Z naught. Our directional vector A is giving us A, B, then C. Sorry, here should be angle brackets. A, B, and C. And as we began, I told you that to fully find the equation of a line, you need a directional vector as well as a known point, one known point. And that is what we've got here. So to find generally any point on the line, which is X, Y, Z, which you don't know, then it's equal to this vector addition here. So therefore, I can have my X, Y, Z in a vector form to be equal to X naught, Y naught, Z naught plus T multiplying our vector A, B, then C, right? So we have X by vector Y, Z is equal to X naught, Y naught, Z naught plus my T, A, B, and C. So now my equations will be X is equal to X naught plus AT, Y is equal to Y naught plus BT, then Z is equal to Z naught plus CT. So these three equations, 1, 2, and 3, gives us what we call the parametric equations of a line. So that's what we call parametric equation, parametric equations of a line. So take note, parametric equations of a line. So now, an attempt to reduce the dependency of the equation on t, which is an unknown. Then how do we do it? You need to make t the subject in each of the equations. So I'll have t in the first equation to be x minus x naught over a, and I'll have t in the second to be equal to y minus y naught over b. Then I'll have t in the third to be equal to z minus z naught over c. Since t are all equal, I can join this and I'll have a new set of equation which does not depend on the unknown z. And this is what we call this. And this is what we call the symmetric equation, right? So the symmetric equations of a line. So this is how we find the equations of a line in 3D. You should have your vector equation generally as, so our vector equation, just have it in mind, which is r, vector r is equal to vector r naught plus what, a multiplying vector at. You can have your parametric, which is given as x is equal to x naught plus at, y is equal to y naught plus bt. Then z is equal to z naught plus ct, right? Then finally, this whole thing becomes your symmetric equation. So take note of that. So thank you for joining me in this video. Hope seeing you in the next tutorial where we are going to solve problems on equations of a line.